So example number 1 on differential equation. That is a problem of the method of separation of variables to solve the first order differential equation. When we told that, show that the solution of the differential equation y dy over dx plus 1 over y squared over 1 plus x squared is equals to 0, given that y is 0 when x is 0, may be expressed in the form y squared is equals to exponential negative 2 tan inverse of x all minus 1. So here, this is the differential equation. You've been given y dy over dx plus 1 plus y squared over 1 plus x squared is equals to 0. So in many cases, the first method, if you want to solve a first order ordinary differential equation, you can see our derivatives dy over dx first order, isn't it? So if you want to solve a first order ordinary differential equation, then the first method to confirm is the method of separation of variables. If the method of separation of the variables does not work, is when you go to the solution, is it linear? Is it a linear first order ordinary differential equation? If it is not that, is when you go to the method of the homogeneous first order ordinary differential equation. So one of the best way of seeing whether the variables are separable, in many cases, if you see x and y, like in this case we have the x and y variables, isn't it? If you see x and y variables are not mixed in any way, then it is very easy to separate them. Like here you just have 1 plus y squared, there is no x there, isn't it? Here you just have 1 plus x squared, there is no y there. They are not mixed. Here if you have y over x, can easily be separated, because here we have one term, only 2 terms. When we have only 2 terms, such kind of cases can easily be separated. We only have 2 terms, it means we can take the other term on the other side of the equation, isn't it? If we take this one term on the other side of the equation, this term here and this, these are 2 terms. So if you take that on the other side of the equation, you will get y dy over dx is equals to negative 1 plus y squared over 1 plus x, positive going on the other side of the equation, it becomes negative. Then you now see you have one term on either side of the equation, isn't it? Are you able to separate them? Yes, because you can see we can bring that numerator 1 plus y squared this side of the equation, then dx goes to the other side of the equation, isn't it? So if dx goes to the other side of the equation, it's like multiplying both sides by dx, and you divide both sides by 1 plus y squared, isn't it? So we are going to get here, we remain with y over dy dividing both sides by 1 plus y squared. So we get over 1 plus y squared to be equals to multiply both sides by dx. Dx goes to the other side, you get dx over 1 plus x squared. Are you seeing you are able to separate it in a manner that y variables are on their own and the x are on their own, isn't it? Are we together? What we've done here is very simple. We've simply multiplied both sides by dx to get rid of dx there, isn't it? Then what we've done again, we've divided both sides by 1 plus y squared, 1 plus y squared to get rid of that, isn't it? So that we've ended up with dx over 1 plus x squared. Then here we've remained with y dy over 1 plus y squared, isn't it? So it means we are able to separate the y variables on their own and the x variables their own. Meaning where there is y, you cannot see x, isn't it? And where there is x, you cannot see y. So that means the method of separation of variables is the method to be applied in solving that problem. Are we together?
What about the negative?
The negative, yes, we have the negative outside here, very good. So we have negative into that, very good. So we have separated the y on their own and the x on their own. So what do? We simply introduce the integral on both sides. Negative can be factorized outside, isn't it? Are we together there?
Yes.
Very good. So if you introduce the integral on both sides, meaning you will be integrating to get rid of that dy with respect to dy with respect to x, isn't it? Are we together? So if you integrate this, what do you get? This is an algebraic substitution. If you go back to what we were doing in integration, this is an algebraic substitution, because if you substitute what's in the numerator to be you will get this what is in the numerator, isn't it? if you let u to be what is in the denominator, you have u, because we have y in the numerator, so it is not resulting into an inverse function. Are you seeing that? So if you have u to be 1 plus y squared, if you differentiate u with respect to y, you get 2. See, if you differentiate u with respect to y, if you differentiate y, you get 0, you differentiate y squared, you get y, isn't it? So you take dy the other side, you remain with du is equals to 2y dy. So it means here we have y dy, meaning we can multiply the numerator by 2 and we divide by 2. Multiply by 2 and divide by 2. So it means when we have 2y dy, we are going to put what? du. And where we have 1 plus y squared is what? Is u. So here it's like we have du over u, isn't it? Are we together? It's like we have du over u. So what is du over u? ln of u. Very good. That is ln of u. So here you can see we have a half integral of 2y dy we found is du over 1 plus y squared is u. We are done with that side of the equation. Then if you go this other side, we have negative. If you integrate the x over 1 plus x squared, you can see this is resulting into inverse function, isn't it? 1 dx over 1 plus x squared is tan inverse of x, because remember, when you have integral of the x over 1 plus a squared x squared, you are supposed to get 1 over a tan inverse of ax. So if a is 1, then you can see dx over 1 plus x squared is tan inverse of x. Where there is a, you put 1. You get that, isn't it? Are we together? Now, having found that, that is what we have on the other side of the equation. So on the other side of the equation, we have integrating dx over 1 plus x squared, we found it is tan inverse of x. Then at the end of integration, you put c. So if you have du over u, what is that? ln of u. But what is u? U is 1 plus y squared, meaning where there is u, you put 1 plus y squared to be equals to negative tan inverse of x. Then at the end of integration plus c. So maybe you can leave c there when you still have integral, isn't it? Then after that, the first thing they want you to make y squared the subject of the formula, isn't it? So for you to make y squared the subject of the formula, you start by removing this a half, isn't it? You multiply both sides of the equation by a half, so that you end up with ln of 1 plus y squared. A half, you multiply both sides by 2 to get rid of a half, isn't it? You multiply both sides of the equation by, so this goes with this, you remain with the negative 2 tan inverse of x. So the 2 times c is just another constant c. It is still just that constant, because a constant is a constant, isn't it? Are we together? Yeah, so even if you say this is c1, then you say 2 times c1 is another constant c. So the constant will always remain the constant, isn't it? Having done that, the next thing is to get rid of the ln, isn't it? Are we together? When ln goes on the other side of the equation, the inverse of ln is exponential function, isn't it? Taking ln on the other side, it becomes, it is the inverse is exponential, meaning we get exponential negative 2 tan inverse of x plus c. Are you seeing that? So if it is plus c, this is loss of indices. So loss of indices, it means we have same base with multiplication sign. That's why they are added. Are you seeing that? Yes. Meaning if you take it back, you will see that here we have where the c is the same as times exponential raised to power c, isn't it? Because same base with multiplication sign, it will mean this plus c. Are you seeing that? Yes. The loss of indices. So you can see exponential c can be another constant, isn't it? You can let exponential c to be, are we together? Yes. To be another
constant.
To be another constant. So having done that, another thing you need to note is what? Or the best way to do that, if you don't get confused, this is what you do. Since constant is a constant, and this side we have, the other side we have tan inverse, this side we have Napierian logarithm, then you can just let that C stand on its own, and you say this is now exponential negative 2 tan inverse of x just plus the constant to make work easier for you. Are you seeing that? Yes. Are we together? Now, having done that, then you now go to the initial conditions. You'll be told y is 0 when x is, meaning where there is y, you put 0, and where there is x, you put 0 to get the value of the constant c, isn't it? Yeah, the reason why you don't take the whole of that c to be on part of the exponential function, because we had two different functions on either side of the equation, isn't it? Meaning if here was ln, here was ln, then the constant would have been ln of c, because everything is an Napierian logarithm. Are you seeing that? If x was exponential function, the exponential function, then the constant there must also be exponential c. Are you seeing that? Are we together? If here was tan inverse, here tan inverse, meaning c must also be tan inverse of c, isn't it? Yes. Good. So having done that, where there is 0, you put y0 and x0. So if you put y0, you get 1 is equals to, where there is x, you put 0. What is the tan inverse of 0? Tan inverse of 0, because where there is x, we are putting 0. Tan inverse of 0 is 0. So 0 times negative is 0. So exponential 0 is 1. Anything raised to power 0 is 1. Are you seeing that? Yes. Exponential 0 is 1 plus c. So what is the value of c? The value of c is 0, isn't it? The value of c is 0. So it means where there is c, we put 0. Are we together there? Where there is c, we put 0. Is that well understood? So having done that, if you put 0 where c is, you remain with 1 plus y squared to be exponential negative 2 tan inverse of x. So for you to remain with y squared as a subject, meaning this positive 1 must go on the other side of the equation, isn't it? So if you take 1 on the other side of the equation, it becomes negative 1. So you remain with y squared is equals to exponential negative 2 tan inverse of x minus, and you've actually proved that y squared is equals to exponential negative 2 tan inverse of x minus 1. Given that ordinary differential equation with the given initial conditions,